Hello students, welcome back. So we are currently now doing this particular module in the course Analog and Digital Electronics. So we already finished 5 sessions here. So let us move on to the next session. So this is basically session 6 of this particular course and specifically the first module. So in this session, this basically deals with introduction of op amps, wherein we deal with the ideal and practical op amp comparisons. Plus we look at some of the performance parameters for the op amps, and then we move on to the applications for op amp circuits. So what are the learning outcomes then for this particular session? Upon successful completion of this session, students will be able to analyze parameters of practical op amp and compare them with the ideal operational amplifier, and then the student should be able to analyze operational amplifier circuits and their applications. There are many applications for the op amp. We will be starting them and trying to do 1 or 2 applications in this session, and then we will continue that in the next session. So moving on then, let us begin this entire discussion by looking at this particular model for a voltage amplifier. So throughout this entire applications, we are basically dealing with voltage amplifiers where voltage is the input and voltage is the output. So you can just have a look at this particular slide over here, wherein we are trying to show you the generalized voltage amplifier module or a model. So what exactly does it have? If you can see here, so this particular thing, it has, okay, so it has a voltage input here, okay, it has a voltage input here, okay, given at the 2 terminals are the input. So this eventually becomes your input to the amplifier, and then you eventually have what we call as the output. Now in this Thevenin equivalent model, we basically have only resistances and voltage sources. So what are these resistances and what are these voltage sources? Let us just go here. So this RS is the impedance of the voltage source that we are going to apply, or the signal source, okay, and RL is the actual load that you are connecting to the output of an amplifier. Then the dotted portion indicates your amplifier, and what all does this amplifier have? Now this amplifier has at its 2 input terminals what we call as the input resistance or input impedance. It is called as Ri. And since it is a voltage amplifier, suppose if it has an open loop gain of A. By open loop, what do you mean? We are not connecting anything from the output back to the input. So if A is the open loop gain of this amplifier and Vi is the input, then what do you expect the output to be? The output would be gain times Vi. So this actually is called as a gain block, wherein it is amplified by voltage by factor of A, and then R0 represents the output resistance of this particular amplifier, and eventually we go and drive the load. So V0 should become equal to, as much as possible, be equal to A times Vi. For that to happen, we'll discuss later, this R0 has to be as small as possible. Okay, so let's move on then and see what is it the case for an operational amplifier and how exactly it looks when you talk of operational amplifier. Now before we go into the actual model of this operational amplifier, or in short what we call this as a op amp. Now why is it that we call this as an op amp? Now as you can see here, you forget the internal diagram for the time being, just see the output blocks. So it is basically having 2 inputs, that is V1 and V2. It is having the inputs Vi, it is called as an inverting input, and Vni, which is called as a non-inverting input, and it has a output. Now bear in mind, all these are what we call as single-ended output notations. By single-ended means we are not showing the common reference for all these signals. So essentially this op amp consists of 2 inputs, okay. First is Vi and ground, the second is Vni and ground. So it always amplifies the difference of these 2 inputs. That's why it's also called as a very high gain difference amplifier, where the output is gain times the difference of the two inputs Vd. So in this case, Vd is nothing but Vi minus Vni, or the difference between the two signals. Now, why this name operational amplifier has come to this particular amplifier? Why don't we just call it as an amplifier? The reason being, now this op amp, because of its versatility, as we will see later when we discuss the parameters in detail, it is used in many applications. Like signal conditioning is the one which comes to mind straight away, means sort of amplifying the weak signal, or a low noise amplifier. We use them in signal conditioning. We use them for integration and differentiation. Plus, we can also use these op amps for operations like summing, which is adding, subtracting, okay, doing a comparison, and it can also do what we call as filtering, which is basically a low pass filter or high pass filter. So because of all these operations that this particular op amp can do, we call it as an operational amplifier. Okay, now coming back to the actual model of this op amp. Now, as you can see, even this op amp also has an input impedance which is given by Ri, okay, or input resistance, which is basically the resistance seen at the two terminals of the op amp. Now, along with that, it is also mentioning something called as the input current Ii and the input current Ini, which are respectively the current at the inverting terminal of the op amp and the current at the non-inverting terminal of the op amp. Now, essentially these two would be 0, and we will see it later again. And then it has the gain block. Since it is a voltage amplifier, okay, it is amplifying the differential voltage here. So AD stands for differential voltage gain, and Vd of course stands for the differential voltage between Vi and Vni. And then, as in the generalized amplifier, it also has an output impedance or output resistance called as R0. So this is net the practical op amp model. Now, if we take this practical op amp and try to do the calculations or try to do the mathematics or the network analysis, it becomes slightly more complex. So rather than that, whenever we are doing any calculations, we go ahead and try to use what we call as an ideal op amp model, which will help us in doing the calculations. But then if you can go back and see, if you do the actual mathematics and use the actual practical op amp, the accuracy difference would not be much. Like it could be, the variation could be around 0.1% or 1% in the values you obtain if you use an ideal op amp model to the values you would actually get if you had used a practical op amp model. So then what is this ideal op amp model? So it will be derived from this particular model itself, but the only difference would be, instead of Ri, we are not going to have any resistance there. Means we are going to say that it is infinite input impedance. So Ri becomes infinite, means there is no connection between the two terminals at the input. Not only that, we also have R0 to be 0 and so on. That we will see it in the next slide as to what is the model of a ideal op amp. So there you go. So that's a model of an ideal op amp. So what do we have basically then? We do not have any resistance here. That means your input resistance is infinite. Infinite means it's an open circuit. Now if your input impedance is infinite, then what happens to your current through the inverting pin and current through the non-inverting pin? They are both going to be 0. Yes, because an infinite impedance means what? You are not going to have any current flowing through that. Not only that, you can observe that this particular R0 is also not shown. It is shown as a short, or in other words, R0 is 0. Okay, so that is the only difference from the practical op amp, and it continues to have the differential gain of AD, plus it amplifies the difference between the two voltages, which is nothing but Vd. Now moving on then, how is it that we can analyze this particular op amp further? Before we go into the applications, we need to see many of the op amp parameters. Okay, we can analyze. So far we have just talked about what? The input resistance and the output resistance. Okay, apart from that, we have so many. Of course, we also talked about the open loop gain. Now apart from these three parameters, there are many other parameters which go ahead and specify a particular op amp. So how to choose a particular op amp for a given application? For example, we told that we have so many applications, starting from integrator, differentiator, just a low noise amplifier, to a comparator and then going on for, let us say, a filter, a summer, a subtractor, and so on. So is it that we use the same type of op amp for all these applications? Maybe, maybe not. So to choose a particular op amp for a given application, we need to understand what are the parameters of interest for us. So to do that, in order to choose a particular op amp, we need to understand various parameters which are there for an op amp. So some of the parameters that we have listed here, we're going to start with telling what is bandwidth, okay, and then we'll go to saying what is the slew rate of an op amp, and then we go to the parameter open loop gain, and then two performance parametrics called as common mode rejection ratio or CMRR in short, and power supply rejection ratio, which is PSRR in short. And then of course the input and output impedances, which you've already seen. Then finally two more parameters which we call as settling time and the offset drifts, which are very important when it comes to signal processing. Okay, so let us slowly take these parameters one by one. For that we need to have a bit of an understanding of how exactly is the frequency dependence of a particular amplifier. So for that, let us move on to this board over here and see what exactly do you mean by bandwidth. Okay, to start with now, first let us try to see what is bandwidth. Now any amplifier that you take, does it work for any range of frequencies? For example, let us say I take a particular amplifier. Now I want to amplify signals in the range 1 kHz to 20 kHz. So can I do it using my op amp? Or suppose if I want to amplify the frequencies in the range 1 MHz to 2 MHz or and so on up to gigahertz. So whatever be the case, there will always be a certain range of frequencies over which I can use my amplifier. So generally speaking, your bandwidth should simply say the range of frequencies over which you can use your op amp. But let us go and give an exact definition of this. To understand that, let us plot the waveform or dependence of gain over frequency. Does the gain remain constant for the entire frequency range, or does it change as frequency increases? So this is going to be a particular graph that I am showing, and these are what we call as semi-log plots. In the sense, you are going to plot the frequency on a decade scale. In the sense, we have 1 here, we have 1, 10, 100, 1000, 10,000 and so on. Okay, that's what we call as a semi-log plot, and on the y-axis we are going to have the gain expressed in terms of decibel. Now what is decibel? Decibel is 20 log AD. If AD is the absolute value, then 20 log, that is log to the base 10, AD is called as a decibel. Now typically at zero frequency, what does zero frequency mean? Zero frequency means your waveform does not go between positive and negative, or it does not have any variations in the cycle, positive half cycle to negative half cycle. So it remains either in positive or in negative. So that we call as a DC. So typically DC would mean frequency of 0 Hz. So let us say we have a certain DC gain of AD 0. Okay, that means what? Or you can even call it as at lower frequencies. At lower frequencies, if the gain is AD 0, then what happens is, if you have an infinite bandwidth amplifier, that would mean what? Irrespective of what is the frequency, this gain is going to remain constant throughout this range from 0 Hz to infinite frequency. But real life is not that way. So what happens is, beyond a certain point, which we call as the 3 dB frequency, or you can even call it as f minus 3 dB. What does that mean? This is the point where your gain drops to 3 dB below its DC gain. Okay, so let me say this is the point typically. So this entire thing is 3 dB. So after that, it sort of tapers at the rate of minus 20 decibels per decade. Now what is this rate called? Minus 20 decibels per decade. Means what? For every decade, means 10 times. Suppose the gain at a certain frequency called f1 is 20 dB or 100 dB. Let us say if the gain at f1 is 100 dB, then at 10 times that frequency, that is at 10 f1, your gain will drop by 20 dB. For every decade it drops by 20 dB. There is another parameter which is expressed, that is something that is called as octave. Okay, so per decade means what? For every 10 times the frequency changes, your gain drops by 20 dB. Now suppose if I want to know a parameter to what extent it falls whenever the frequency doubles. Okay, so let us say if the frequency is f1 and then it changes, then you want to know what is the gain at 2f1. So at 2f1 it will be 6 dB lesser. Okay, we also call it as OR. Okay, there's another parameter, 6 dB per octave. Okay, what does this mean? For every double the frequency, your gain drops by 6 dB. Suppose if the gain at f1 is 100 dB, then what would be the gain at 2f1? Okay, with this definition that we just now said, if the gain at f1 is 100 dB, what will be the gain at 2f1? Means at twice this frequency, right? Should I use this one or this one? I have to use minus 6 dB per octave. So that would mean 100 minus 6, which is 94 dB. Likewise, if I want to find out what will be the gain at 10 f1, how can I do that? Simply go and find out what is the value at f1. At f1 it is 100 dB. So at 10 times that frequency, obviously your gain will reduce by how much? By 20 dB. So 100 dB minus 20, so this is going to be 80 dB. So this is called as the frequency dependence of your op-amp. This is a very important parameter or a very important relationship which you have to understand. Of course, we are showing here it by straight lines. Actually, this curve is what we call as an asymptote. The real curve would be considered at 3 dB less, right? So it will be something like this, wherein it will be less by 3 dB. But we try to approximate it by using an asymptote. Okay. So let's move back and then try to see what are the other parameters that we have to understand. Now, what does it mean by bandwidth? Now, at some point of time, this gain will go and cross 0. Okay. I mean it reaches unity. So if AD is 1, okay, if you want to have a gain of unity, if AD is 1 and if I want to express it in terms of decibel, how much would that be? Okay, this would be 20 log of 1. What is log of 1 to the base 10? Okay, so that would be 0. So that means what? In this curve, whenever I point 0 dB here, after that it starts going negative. Okay, there will be a certain point wherein this curve will cut this 0 dB line. Okay, now this 0 dB frequency is called as unity gain bandwidth. Okay, means what? If the gain is 1, which amounts to 0 dB here, if the gain is 1, what is the frequency at that point? I call that as a unity gain bandwidth. Okay, so whenever we say the word bandwidth, specifications or data sheets refer to two types of bandwidths. One is they usually give what is called as a unity gain bandwidth or UGB, or this is also called as gain bandwidth product. For any op-amp, your gain bandwidth product will never change. What is the gain bandwidth product? Gain multiplied by bandwidth, that will never change. If you increase the bandwidth, your gain has to reduce. If you decrease the bandwidth, your gain has to increase. So net, your gain bandwidth product is always constant, which is always equal to your unity gain bandwidth. Why? Because gain is 1, so 1 into this. So this UGB is one parameter which is usually seen in many data sheets. Now apart from that, there is something called as bandwidth, the range of frequencies over which you can amplify with the same gain. Now amplifying with the same gain is rolled out, right? Your gain initially was at AD0, then it eventually starts dropping, let us say to the point till it drops to minus 3 dB. Now this entire range of frequencies I call as the bandwidth of my op-amp. What does that mean? I can suffer a gain loss up to 3 dB, but nothing beyond that. So up to 3 dB I can use this. That means what? I can use my op-amp all the way from 0, that is DC, to a f minus 3 dB frequency. So this is called as the bandwidth of an amplifier. So two parameters, do not get confused. Bandwidth is from 0 to f minus 3 dB, and unity gain bandwidth, which is also referred to as a gain bandwidth product, is the frequency at which the gain curve cuts the 0 axis. What is 0? 0 actually corresponds to a gain of 1. When expressed in terms of dB, it becomes 20 log 1, which is 0. So this is as far as bandwidth is concerned. This is the explanation. Now let us move on to the next parameter, which is called as the slew rate. Now whenever I am using my op amp in signal conditioning circuits, what does signal conditioning mean? I am giving an input which needs to be amplified. Okay. So let us see, for example, let us give a unit step function to this particular op amp. So I will again try to draw a curve here. This time bear in mind, I am trying to see its transient response. Okay. So this is what it's going to be like. This is with respect to time, and this is your applied voltage input. So suppose let us say at some time t equal to t1, okay, I change the input from 0 to 1. Okay. At time t equal to t1, I change the input from 0 to 1. Now output initially was also at 0. Now the moment the time it changes to 1, can my op amp directly change to 1? Practically speaking, not possible. Why? Because whenever you apply any signal to a circuit, it takes some amount of time for it to be amplified and then coming out, which we call as a typical delay, right? So typically what happens is, this particular op amp, let us say it starts rising and it overshoots, right? It shoots up, it does not settle at 1, it sort of shoots up and again comes down and does a hunting phenomenon, and it eventually settles to 1. Okay, this is called as the transient behavior of your op amp. Now with this behavior you can analyze many things. First let us talk of slew rate. Now what is slew rate defined as? Now slew rate, okay, as the name suggests, slewing, right? What is the maximum rate of change of output of an op amp? For example, this was your V0, okay. Now V0 is changing from 0 to 1 and it is saying a certain amount of time. So what is the maximum rate at which it can change? It is usually expressed in terms of volts per microsecond, meaning what? In 1 microsecond can I change to 0 to 1 volts? In 1 microsecond can I go from 0 to 3 volts or 0 to 10 volts? So that depends upon the type of op amp you are using and whether it is a high speed op amp or a low performance op amp. So slew rate then is defined as the rate of change of the output voltage. Rate of change would mean per time. So that's what is shown here in terms of microsecond. So let us say this has a certain slew rate of V1. Now suppose if you have another waveform which rises very slowly, okay. So what does that mean? This has much more smaller slope, right? That means the rate of change, the amount of change in the output per unit change in time is lesser as compared to the first one. That means what? The slew rate here is higher than the slew rate here. That's what we mean. It's just a slope of voltage versus time, dV divided by dt. That gives you the slew rate, the rate at which you can change. So this curve over here has a lesser slew rate than the one which we have drawn in the first. This is one parameter which we would like to look at. Now whenever I want to have a very high performance op amp, what does that mean? I would like my input to react, the output to react very quickly to changes in input. So which one is more quicker? The first curve or the second curve? The first one, right? Because it's reaching that one in much lesser time compared to the second one. But there are some drawbacks which we will see later. The one which rises fast also has a larger overshoot. See here, the one which rises slowly has a much smaller overshoot. So again, these are all various trade-offs that we have whenever we are deciding a type of amplifier or op amp which we would like to use. Then moving on, the next parameter here, settling time. Since we are with this curve, we know that the output, instead of directly going to 1, it is having a small overshoot and then it sort of rings and eventually settles down. Now to reach the final value of 1, it may even take infinite time. So I can't wait till infinite time or large amount of time to reach that output voltage. So instead what do? I basically look for a small tolerance band around the output voltage which it is expected to reach. In this case, it is expected to reach our output of 1, which is a unit step function that I am giving. So let us say the moment the output reaches within 1% or 0.1% or 0.01%, as the case may be. Okay, so it is 0.1% of the range. So it's here it is beyond the 0.1% band. Okay, so somewhere here it reaches this band. So this I call as the time Ts. So T1 to Ts, this time becomes my settling time. That means what? The time it takes for the output to reach within a known tolerance band. Usually it is 0.1%, or in some case it can also be defined as 0.01% based on what is the accuracy you are expecting for a particular op amp. So we have seen now slew rate, we have seen the overshoots, what happens, and we also seen what happens to the settling time. So the slower the op amp, what will happen is the longer it takes to settle. So a slower op amp would also have a longer settling time apart from having a slower slew rate. So this takes care of the parameters called as settling time. Now with this then we can then move on to the other type of parameters. This is the one more to do with the transient phenomenon. Now let us look at the two things. So the input impedances and the output impedances were already seen in the op amp model. We saw the practical op amp model wherein we showed Ri as the input impedance, which is the impedance between the two input terminals, and we also displayed R0, which is shown as in series with the gain particular block, or the voltage gain block AD times VD, which is the difference of Vi and Vni. Now moving on, are there any other parameters that we need to discuss? Okay, the open loop gain is also discussed as AD, which is basically nothing but your V0 is the output and Vi minus Vni. Okay, the difference between the two pins, which we typically call as Vd. So open loop gain is simply the ratio of the output voltage to the difference voltage at the inputs. Now apart from this, we have two most important parameters for any op amp. The first one is called as CMRR. Okay. Now CMRR is defined as, the acronym stands for common mode rejection ratio. Now what does common mode mean? Okay. Now as we said, AD is the difference mode gain, means what? It's only amplifying the difference signal. Now apart from that, we also have one more definition which we call as common mode gain, meaning what? What is the gain of this amplifier to the common voltage? So common voltage is given by what? Vc. Now just like Vd is given as difference of Vi and Vni, Vc is nothing but an average of these two, Vi plus Vni divided by 2. So the common mode voltage means it's the average of these two voltages, which is Vi plus Vni divided by 2. So technically speaking, right from the beginning we have been telling that op amp is a difference amplifier, a high gain difference amplifier. Means what? It should not amplify the common voltage, it should only amplify the difference voltage. So that being the case, ideally speaking, I would like to have this to be 0. I should not be amplifying any common mode voltage, whereas this should be as high as possible, because we say it's a high gain difference amplifier. Now is there a parameter which can tell the ratio to which it amplifies a difference signal and the ratio to which it amplifies the common mode signal? Now that ratio is called as common mode rejection ratio. It is expressed as the difference mode gain to the common mode gain. Okay. So CMRR is then the ratio of difference mode gain to common mode gain. Again, usually it is expressed in terms of decibel, meaning what? If you want to write CMRR in decibel, what does that become? Right. So it becomes 20 log AD by AC. Okay. So this is the CMRR when expressed in terms of decibels. Now after this, understanding all these parameters, we'll go back and try to compare the parameters between ideal op amp and practical op amp. So when I talk of ideal op amp, I should not be having any common mode gain. So common mode gain should be 0. So if common mode gain is 0, what will happen to this term? AD upon 0, which has to be infinite. Okay, that we'll see later again. So the next parameter that we are looking at, now of course this common mode rejection ratio, it has another definition which we will see later when we talk of offsets. Okay. So the next parameter is called as PSRR. Now what does PSRR stand for? PSRR stands for power supply rejection ratio. Just like CMRR said, to what extent it is rejecting the common mode signal and only amplifying the difference mode signal. Likewise, whenever I am using the circuit for amplification, if there is a variation in the power supply voltage, okay, your VDD, VSS and so on, if there is a variation in the power supply, does it affect my output? Ideally speaking, it should not. It should be totally independent of the power supply variations, of course to an extent. So a parameter which defines this is the extent to which the output voltage changes because of change in supply voltage. So let us say the change in supply voltage would be delta V plus. Usually we have V plus and V minus. Like typically op amps are, we say dual, they require dual power supply. They require a V plus also and they require a V minus also. So normally we have PSRR plus and PSRR minus, which is for positive supply and negative supply. So if you have positive supply, it changes by an amount called delta V plus. Now to what extent does your output voltage change because of this change in power supply? Okay. So ideally speaking, should my voltage change with change in the power supply? It should not, because it has to be independent of changes in the power supply. That's when I say it's a very stable op amp. So in that case, for ideal case, this delta V naught will be 0. So PSRR would again be some finite value upon 0. It would again be infinite for a ideal op amp. Likewise, you can also define PSRR for a negative power supply. In that case, it would be PSRR minus, and we'll have the variation in the negative of the power supply to the change in the output voltage. So these two parameters, CMRR and PSRR, are very important parameters which give us to what extent I can reject the common signal and to what extent I can reject the changes in power supply or the noise in the power supply. The last one that as a parameter that we are going to discuss today is something which is called as an offset voltage. It's again a very interesting topic. Now let us assume or let us imagine an op amp, right? So a typical op amp would be something like this. Okay, it will have an inverting terminal and a non-inverting terminal. It will have the power supplies connected, which is V plus and V minus. Okay, it has an output voltage called V naught. Okay, and the two inputs, first one is Vi, input at the inverting, the second one is Vni, which is the input at non-inverting. Now suppose at any point of time, let us say if AD is the open loop gain, what is V naught given by? It is given by AD times Vd. Now suppose if I short these two terminals, what do you think will happen? Okay. So by doing that, what am I ensuring? I am ensuring that both my Vi and Vni are one and the same. So if they are one and the same, what do you expect Vd to be? Your Vd would be 0. So if your Vd is 0, then I expect that my V naught also to be 0 volts. This is how it is expected to be. But in real world or in a practical op amp, this does not happen. Even when you short the two inputs, you are going to have a finite voltage. It could be millivolts, it could be microvolts or whatever it is, but it is going to have a small voltage which we call as output offset voltage, VOS. So what is VOS then? The output that you are going to get when you short the two input terminals. Remember, I keep saying two input terminals because we are only referring to single ended inputs. At no point of time we are referring the common reference. What is Vi actually? Vi is the voltage applied between this terminal and the reference or ground. Then Vni is the voltage between this terminal and the reference ground. When single ended notation, again output is the voltage between V naught and the same reference. But in single ended notation we never talk about that. Okay. So when we short these two terminals, okay, then what happens is non-zero voltage comes, that we call as output offset voltage. Now can you make some corrections to this and ensure even in a practical op amp that we can make this 0? Yes, it is possible. How? To do that, what I will do now is, I will now apply a small voltage here which I call as VIOS. It could be plus or minus, minus or plus, whatever. It can vary whichever way you want. Now we go on varying this voltage source till such time this becomes 0. Okay, I'll repeat what I'm trying to say. Now by shorting these two, I'm having a non-zero output voltage. So if I want to have a 0 output voltage, what do I do then? I go and put a small correcting voltage there, go on varying that either on the plus side or the minus side till such time this VOS becomes 0. Now that voltage when the output becomes 0 is called as input offset voltage. Okay, there are two terms here. One is the output offset voltage, which is nothing but the voltage that you get when you short the two inputs, and the other one is V input offset voltage, meaning what? The voltage you have to give at the input terminal to make the output 0. Okay, and these are typically called as offsets, means they are all non-idealities of your op amp. You would like to have them 0. So in an ideal op amp, VOS would also be 0. Then you don't need VIOS at all. So even VIOS would be 0. So this is as far as the parameters is concerned. Now that we have seen all these parameters, let us go back and see what is the ideal value of these parameters and what is the practical value of these parameters. For that we are going to use an op amp which is op amp IC 741. Okay, it's an 8-pin IC which is an op amp IC 741. So let's go here and try to see whether we can compare this particular thing. Okay, so the comparison goes here in this way. There you go, right? So what we are trying to do is we are trying to compare the ideal op amp with a practical op amp. The example that we have taken here is called as IC 741. Starting with bandwidth, right? An ideal op amp should have a bandwidth which is infinite, right? In the sense, as we were to amplify the entire range of frequencies right from DC all the way up to, you can say infinite or 1 gigahertz or whatever the case may be. But in real world, it's not possible. So IC 741 has a bandwidth of 1 megahertz. The parameter that we are referring here is what is called as a unity gain bandwidth. Okay, not the 3 dB bandwidth. Next, slew rate. So when it comes to slew rate, an ideal op amp should be able to go from 0 to 1 in 0 amount of time. In other words, I can change in 0 time. Changing in 0 time is what? Volt per microsecond. So 0 time changing means it's infinite slew rate. But practically speaking, you can only change by about 0.5 volts in 1 microsecond for a low performance op amp like 741. If you want a faster response for signal processing, you have to go for other high performance op amps, okay, which we are not discussing here. Next, the open loop gain. So far what we have done now, we have seen what it is for an ideal op amp, and then we have seen what it is for a practical op amp vis-a-vis the two parameters which are bandwidth and slew rate. So bandwidth is done, okay, slew rate is done. Next is the open loop gain. The open loop gain for an ideal op amp is infinite, in the sense what? The gain as large as possible. It's so huge that I can call it as infinite. But in real world, you're not going to have such a huge gain. You are going to have something called as, for every 1 millivolt change in the input, I can change by 200 volts. But bear in mind, we can never have an output which is 200 volts. Okay, it's just a parameter. Why we can't have an output which is 200 volts? Simply because the largest value of the output can be what we call as a saturating output, which is at best equal to your power supply voltage V plus, or when it is minus, we said it is V minus. This we'll again see when we discuss the open loop comparators. Moving on, next one would be CMRR. So CMRR, as we said, what is CMRR? It's a ratio of difference mode gain to common mode gain, that is AD upon AC. So ideally AC should be 0 and AD should be as large as possible. So we're looking at a situation where the denominator is 0, so CMRR is infinite for a ideal op amp. Whereas in terms of a 741, it's a very large figure which is again expressed in terms of dB. It is going to be around 100 dB, which is around 90 to 100 dB. Then coming on to the power supply rejection, again, no matter to what extent the voltage supply changes, the output voltage should not change. So PSRR was delta V plus or minus divided by delta V naught. So delta V naught should be 0, so ideally it will be infinite. So practically it will be pretty high on the order of again around 100 dBs. Then the two most important parts whenever we talk of amplifiers, it's the input impedance and output impedance. So input impedance is infinite in case of an ideal op amp, whereas it's pretty high in the range of a few mega ohms for 741. Likewise, the output impedance is 0, okay, whereas it's a few ohms in the order of like 100 ohms for 741. The settling time for an ideal op amp, okay, the moment I apply the step input 0 to 1, immediately the output should change. Why? Because it has an infinite slew rate. So in 0 time it reaches 1. So that's ideal case, but in real case nothing can happen in 0 time. We have around 0.5 microsecond for a 741 op amp. That means it takes around 0.5 microsecond for the op amp to settle within a known tolerance band, which is usually around 0.1% of its final value. And the last one is the input offset voltage. Means remember, what is the voltage I have to connect at the input to make the output 0 while shorting the two inputs. Okay, for an ideal op amp it is 0, whereas for a practical op amp or a 741 it is around 2 millivolts. So this gives us a big picture as to how close I am to an ideal op amp. As you can see here, the parameters are pretty much okay as far as IC 741 is concerned. Now that we have seen all these parameters, let us move on and see some of the applications that we can take for these op amps. Okay, as I said, operational amplifier, it can do many operations. So let us try to see some of those in this session. Let us start with the first one, which we call as a peak detector. The peak detector is something which is used in demodulation, right? So for example, whenever I have an AM signal, I modulate that using high frequency. I just want to know the peak of the output. That is where my modulating signal is. So for such application we have peak detector. Then we will see something called as comparators, okay, and then the active filters. We will also see what do you mean by filters and what are all these. Then we will see the oscillator. We already seen one oscillator when we discussed JFET. This time we will use an op amp to do the same. And then we will discuss an application for non-linear amplifier. So far all the applications were linear, okay. So this is the circuit diagram for a peak detector circuit. So what does this circuit essentially have? Let us for the time being ignore the circuit that we have on the right side, okay. Let us only concentrate on the circuit on the left side. Now what is this particular circuit configuration here? Okay, if you can see here, we are applying the input voltage to the non-inverting pin of the op amp, whereas at the output of the op amp we have a diode, okay, and we have R2 in the feedback path, and we have a capacitor and another resistor R. Typically R is very large, R2 and R1 are quite small. Now before we analyze this circuit, let us see what is the expected input and what is the expected output. The type of input that I am looking at is something like this. It is going to be a certain frequency, okay, the peak of which is going to change, okay. Now I only want to see what is the peak. You can see here initially the peak is this, okay. I will try to change the color here. Initially the peak was here, and then it is here, and then it is here. So I should get a waveform which increases slowly with every increasing peak at the input. This is the requirement at the output. So I give the input as a red signal, I should get the output as a blue signal, which is essentially the peak. Again, if the peak falls, it goes on falling. Now this circuit is the one which can only detect the positive peaks. For example, let us say if again my input falls here, if my input falls, then what do I expect my peak to? My peak also it sort of falls. It tries to catch the peak every time. That's the meaning of a peak detector. Now this being the case, let us start the analysis now. Now initially let us assume that the output is 0, right? The output is 0 means what? This capacitor is also totally discharged. The output here is initially 0, okay. So if the output is 0, okay, what is it that I am feeding back at the inverting pin? At the inverting pin I am feeding a very small voltage, which is actually 0 voltage, whereas at the input I am having, at the non-inverting input I am having a positive voltage. Now a positive voltage at the non-inverting pin vis-a-vis a 0 volt at the inverting pin means what? The output becomes or tries to be on the positive side. It tries to go towards plus Vsat. So what's happening is the output becomes positive since input at plus is larger than the input at minus. We already analyzed this when we discussed the IC 555 timer, wherein I gave you a brief intro as to how a comparator sort of a phenomenon works, right? When the input at plus is higher, then the output becomes plus. When the input at minus is higher, then the output becomes logic 0 or minus Vsat, as the case may be. Now here, since the voltage at non-inverting pin is 0, it starts to rise, right? The output starts to rise. In the sense what? The diode is now forward biased. If the diode is forward biased, what will happen to this capacitor? The capacitor starts charging. The capacitor starts charging and reaches a positive volt. Let us see it reaches this particular peak here. Okay, it reaches this particular peak here. Now let us try to use a different color for this so that we know what exactly is. Okay, so that we can redraw the entire thing here. Okay, so that we can just concentrate on two peaks here. Let us say initially this is the peak and then this is the peak. Okay, let us concentrate first on, let us say initially it is input is 0, then it can charge all the way up to this point, right? The capacitor charges to this point. The moment the capacitor charges to this point, the input goes below this point. So but since the capacitor is charged to this voltage, I will call this voltage as peak as V1. Since the capacitor is charged to V1, the capacitor charges to V1, after that the input falls below V1. The moment the input falls below V1, then what happens to the input here? The input here now V1 is greater than the input at non-inverting terminal. Okay, it is greater than the input at non-inverting terminal. So what happens to the output then? Output becomes minus. In the sense, this diode now becomes reverse biased. So if the diode is reverse biased, can the current continue to flow and charge this capacitor? No, this is cut off now. If the diode is reverse biased, I am having a negative here. So diode is reverse biased, I can't charge the capacitor. But does that mean that capacitor will hold the charge forever? No. It then can discharge through this resistor called R. Now typically this resistance is kept very large so that it discharges very slowly, okay, or it can hardly discharges. The design goal to find the value of this resistance is how quickly you want the second peak to come at the input. So it should not discharge till that time. It should only discharge when the input peak also falls. So if I have very high time constant in the discharging, the voltage here remains constant till the next peak comes, or it discharges very slowly. Okay. The moment I have the next input peak coming up, if it is larger, again the diode becomes forward biased because the voltage at this pin is now larger. Diode is forward biased, again it starts to charge and then it can catch the new peak here. So this way, successfully while the capacitor is charging, it can go on catching the peak and it can stay at that peak. Next, if the peak at the input falls, okay, let us say if the peak at the input falls, so this is what is happening. The peak is falling, let us say the peak falls. So let us say the peak falls to here like this. Now what is happening is, it was discharging very slowly, right? So it's slowly discharging and then it can catch this peak. If we were not allowing this discharge to happen, then my waveform would remain at this point. But now I have to allow it to discharge, so I choose an appropriate value of R. So and then again it can catch this peak and so on and so forth. So this way you will end up having a circuit which can detect a positive peaks at the input. This is a peak detector. Now coming to the one which I had asked you to ignore, why is it that I need to have this circuit here? Remember, my capacitor is supposed to discharge very slowly. Now suppose if I connect this directly to my load resistance, okay, suppose if I connect directly to RL here, what can happen? The capacitor can start to discharge through RL, right? So to prevent that, we have what we call as a buffer circuit. What does a buffer circuit impose? The buffer circuit, it shows a very high input impedance here. Okay, it isolates the load from the input or this RC, so that the capacitor does not discharge through RL. It gives a buffer for this particular circuit. So net, what does your peak detector have? Your peak detector is having one, at the input it's having a peak detector circuit which is typically a diode connected to non-inverting input. I mean a diode connected to the output and the input applied to the non-inverting terminal of the op amp, plus a buffer at the output to ensure that the capacitor does not discharge whenever the peak is falling. So this is in net the circuit for peak detector. Moving on then, let us go to the next set of experiments, which a next set of applications, which are basically what we call as comparator applications. Now this comparator, let us start by an example which is called as a zero crossing detector. Now what does this zero crossing detector mean? This basically means can I have a circuit which can tell me when is it that I am crossing a zero? Am I going from plus to minus, or I am going from minus to plus? Whenever I cross 0, I want the output to change from plus to minus and so on and so forth. Now again, this is a circuit configuration wherein we apply the input to the non-inverting terminal and the output, there is no feedback, it is open loop. Okay. Now we will come to why we require this D1 and D2 later. For the time being, let us concentrate on how this works. Now this inverting terminal is always grounded. Now let us say, suppose initially if Vi is 0, so if Vi is 0, my output also would be 0. You can see on the curve here, because both are 0. The moment the Vi becomes greater than 0 or it crosses the 0, what do you expect? The voltage at the non-inverting terminal is becoming higher than the voltage at the inverting terminal. So this causes the output to saturate to plus Vsat. Okay. On the other hand, if the voltage falls below 0, then the output saturates to minus Vsat. So this is the region when it is greater than 0, this is the region when it is less than 0. Then why do we have these input diodes at the input? I don't want any heavy voltage or a large signal at the input to destroy my op amp, because op amp when is open loop, even a few microvolt difference can cause the output to saturate. So any large signal that comes at the input, it's either bypassed through D1 if it's a positive input, or it is bypassed through D2 if it is a negative input, thereby not allowing any voltage to be applied or any current to go into the op amp and destroy that. So this being the case, what is the waveform look like now? The waveform will now look like this, right? So whenever your input is crossing the positive voltage, okay, this is the input signal applied. Whenever input is positive, which is in this case, the output is plus Vsat, and whenever the input crosses the 0 towards negative, the output also crosses and changes to minus. So from plus to minus, the circuit is changing. This is called as a zero crossing detector, and this is essentially what we call as a non-inverting zero crossing detector. So this is what we have done so far. Let us quickly summarize what is it that we have done in this particular session. So we have discussed the op amp performance parameters vis-a-vis the practical op amp and the ideal op amp, and so what's the difference, and we listed the applications that we will be doing, and we also saw two applications, that of a peak detector and of a zero crossing detector. In the next session we will continue with this, and we will go on and see few more applications, and we will also do some numericals based on the characteristics. Okay, thank you.